Welcome to your very first AP ECE Econ Chemistry homework review with me, Mr. Wilkosz. This one is for the problem set from the textbook for Chapter 6, Electronic Structure and the Periodic Table. We've got a slew of problems to look at, so let's dive right on in. Problem 3. You're asked to consider in this problem a specific line that comes from the spectrum of neon, and you're given the wavelength as lambda equals 837.8 nanometers. You're asked to find where on the span of the electromagnetic spectrum this particular wave fits. So to facilitate this process, I advise converting the value given to you in nanometers into meters, and then comparing with a given spectrum, for example, out of your text. You'll be able to find that with this particular line having a wavelength of 8.378 times 10 to the negative 7th meters, it fits just to the right of our visible spectrum within the infrared portion of the electromagnetic spectrum. Part B of this problem asks you to find the frequency of that same piece of light, that same wave of light. Using the equation c equals lambda nu, the speed of light c equals the wavelength lambda times the frequency nu, and a little bit of algebraic rearrangement, you can plug in values to find that if you divide the speed of light by that wavelength in meters, so you can cancel out your meters units, you will be able to find that the frequency is 3.578 times 10 to the 14th per second, which is the same as hertz, which is the same as seconds to the negative 1. In part C of this problem, you're asked to find the energy, but not just the energy of one photon from this particular transition, but the energy of a whole mole of photons from this particular transition. So my advice is to find the energy of a single photon first by using the equation E photon equals h Planck's constant times nu, the frequency. And when you plug that in, you can find that a single photon has the energy of 2.371 times 10 to the negative 19th joules. That's per photon, very small amount. Using a little bit of dimensional analysis, we can convert that unit of photons into moles of photons and joules into kilojoules. Let's take a look at that. So you take that given value from the previous slide and convert into moles of photons and convert into kilojoules, and you'll find out that the value is 142.8 kilojoules per mole. Let's take a look at problem 9. Alright, so you're considering a transition, assumedly of hydrogen, between energy level n equals 4 and n equals 2. You were asked to find the frequency of this. So you use the Rydberg, or a variation of the Rydberg equation, where you have frequency equals the Rydberg constant divided by Planck's constant h multiplied by 1 over the low energy level you're considering squared, subtracting 1 over the high energy level and high that you're considering squared. When you start to plug in and populate that equation with values, you get 2.180 times 10 to the negative 18th joules divided by 6.626 times 10 to the negative 34th joules times seconds. And then here we've got n low, which is 2 squared, and over here we've got n high, which is 4 squared, the higher energy level and the lower energy level respectively. When you solve that out, you find that the frequency is 6.169 times 10 to the 14th per second, or hertz. Where does that fit on the electromagnetic spectrum? We play the same game that we did with the previous problem. We take that and try to find a wavelength for it, and we use the equation, the speed of light equals lambda times nu, and through converting that into nanometers, we can find it's 486 nanometers, which actually is in our visible spectrum, and we can see that literally and figuratively. If we check out this particular slide here, we can see that that 486 nanometers would fall in the blue-green section of the visible spectrum. Part C of this problem, we're asked if energy is absorbed, and the answer is no. Energy is emitted in this one. The transition that we're considering is from here, energy level 4, down to energy level 2. So from 4 up here down to energy level 2. So we actually should see energy emitted, and that's why we see light from this particular transition.